Welcome to Introduction to EMC first web seminar. We'll have a series of web seminars focusing on EMC. This is the first web seminar intended to give you an introduction to EMC, or what's called electromagnetic compliance. So before we start the presentation, we just need to understand what is EMC. EMC, or electromagnetic compatibility, is the capability of an electronic system to function compatibly with other electronic systems and not produce or be susceptible to interference. A system is considered electromagnetically compatible if it does not cause interference with other systems, it is not susceptible to emissions from other systems, and it does not cause interference with itself. It's like living in peace and harmony with your neighbor. Don't shoot your neighbor, don't let your neighbor shoot yourself, or don't shoot in your foot. Now, designing products for EMC are not only important to the operation of the device in its intended environment, but also to meet regulations in the various countries where the product is sold. Most countries around the world today have some sort of EMC regulations. Unfortunately, the problem with regulations is that they are very carefully set the desired limits and test procedures for EMC, but offer no guidance on how to meet these limits. These regulations also don't tell you why the limit is important. So we'll try to address some of those deficiencies in this series of seminars. Now, when we talk about EMC, you will hear lots of acronyms, and people interchangeably use many of them. One of them is like EMI or RFI. Many times in the past, subject matter was referred to as an EMI or RFI. EMI is an electromagnetic interference, while RFI stands for radio frequency interference. RFI is like a subset of EMI. Then design community created the term EMC to more positively refer to these conditions. Now, when we talk about an EMC, you can divide in three different sections or three different groups. One is source or emitter that generates the noise. Then that signal or interference is transferred through a coupling path. So you have a transfer path. And then there is a receptor or receiver system that's susceptible to those interferences. And this is a typical composition of EMC. When we talk about various EMC subgroups, they either focus on a source, so you limit the total amount of interference signals you are generating, or they focus on receiver, so you make your receiver immune to all the interferences. Like if you look at some of those examples, you can think about a radio station. Radio station transmits a signal, and that's an intended signal. But if another radio tuned to a different frequency, and if it receives the same signal, then it becomes an unintended signal. So you may have a condition where you have an intended emissions or as well as an unintended. So now again, if you look at some of those subgroups in a little bit more detail, the first one is emissions, but in this case is a radiated emissions. What we have is a noisy component, and that's generating all the radiation. And then depending on the environment, you may have another receptor that is susceptible to those noise. In the second case, like if you had a radiated emission from the first group, and in this case you have a potentially susceptible component that picks up the noise and is being interfered in normal operation. Third is conducted emissions. In this case, again, you have a noisy component, but instead of radiating noise in the air, it's generating a noise through a conducted path. It can be like a power line, cables, and that creates an interference with another object. So that creates our fourth case where you have a conductive susceptibility. So the conducted noise generated by the first object now is creating a problem with this object that's potentially susceptible to the noise generated through conductivity. Now when you look at EMC, it's such a broad term, so let us look at some of the popular instances of EMC. The first one is called emissions. Here the intent is to protect nearby receivers. In this particular example, we have one transmitter, and that may be an unintended transmitter, and that's causing interferences with other objects, like in this case some automotive examples, or as well as a test equipment and possibly an aircraft. So in this case of instances, what we want to do is we want to limit emissions generated by the transmitter. You block them at a source. Here, as just in a figure, we have used a cage. If you really talk about it in a technical way, then you can use something like a Faraday cage to limit the emissions. The next case is an opposite to that one. In this case, instead of limiting emissions at source, we are trying to make receiver or susceptible component that is having issues with the radiated noise more robust or more immune. So here, if the system is more robust, then it may not be interfered by the other transmitters. So then this is a typical way of most of the EMC standards. One way is you try to make word ideal by, like in first case, you limit an emissions on interference from the source itself, and the second case is where you assume that there is a problem and you try to make the system more robust, and that way you see all kind of regulations. The next one is an ESD, or electrostatic discharge. Like in this case, a person who is walking on the carpet, they may generate enough static charge, and when they touch a metal object, the charge gets transferred to that metal object, and that creates an electrostatic discharge event. This voltage can be really high. It tends to be in the kilovolts, and most of the time it's a really fast discharge. And typically, whenever there is a man and machine interface, you may see a problems due to an ESD. We'll have some seminar that we focus only on ESD, and we get into more detail on ESD in upcoming seminar. The next one is electrical fast transients, or a power disturbance. In this case, it's a power disturbance to an equipment. In your house or industry, you have a power line, and you may have multiple systems or equipments connected to the same power line. That creates a case where you may have one noisy component that generates lots of noise. Like as an example, anything that has an inductive load, like motors, when they are running or when they are switching inductive load, it creates lots of noise on power line. And if you have another equipment connected on the same line, like in case there is another appliance connected to the same line, that may be susceptible to the same noise generated by another equipment. So here in this instance of EMC, the intent is to protect the receiver or an equipment from any disturbance on a power line. The next instance is like an opposite to that. In this case, we want to limit interference generated by an equipment on power line. So this case is reverse. If all the equipment controls the amount of noise they put on a power line, then you don't need any the second case like electrical fast transient protection or immunity. A classic example is like a switch mode power supply. And switch mode power supply, during its operation, it generates lots of noise on power lines. And on most of the switch mode power supply design, you will see a line filter. That line filter is intended to reduce the amount of noise that is being fed back to the system, being fed back to the power line. Now next one is a power surge or indirect strike lightning. You get a power from typically cables. It may be underground or it may be overhead, and lightning may strike those cables, and that can create an indirect strike of lightning for whatever equipment or system that is getting power from the power line, and that's called a power surge. Power surge can be a huge problem because the current maintains, we are talking like a 50,000 amps kind of huge current, and that event is much longer in the time duration, and that can have a significant impact on the system. And just to give you an idea, this topic is a huge subject. I have one more. Next one is an electromagnetic pulse. So when there is a nuclear bomb explosion, it's a huge electromagnetic effect, and that can also have a devastating effect. And that's all part of an EMC or electromagnetic compatibility. Definitely we will not discuss anything about EMP in this class. We have looked at some popular instances of EMC. Now let us look at some of the regulations that define or drive various requirements for those instances. There are tons of regulations or standards that define various EMC requirements. Some of them are like FCC, Federal Communication Commission, IC, International Electrotechnical Commission, military, medical, vehicular, and so many other standards. And as it is said, there's one good thing about standards, there are a lot of them to choose from. The first thing is FCC, or Federal Communication Commission. It mainly focuses on emissions. Any unintentional radiator, device, or system that generates and uses the timing pulses at a rate in excess of 9,000 pulses per second and uses the digital techniques must meet FCC requirement. FCC is a legal authority. If you want to sell your equipment or system in United States, you must meet an FCC requirement. The FCC defines two classes. Class A, marketed for use in commercial and industrial or business environment, and Class B, that's for equipment or systems marketed for use in residential environment, but includes use in commercial or industry or business. So the Class B requirements are more stringent than Class A. It's believed that residential users have a lesser expertise or resources to fix an issue that may be generated due to an EMC. Next one is IEC, International Electrotechnical Committee. It's an international body that processes regulations to facilitate trade between countries. It creates two kinds of standards. One, to address various environmental conditions, and second, to take care of many products. And when most of the product level standards refer to original environmental level standards. One difference between FCC and IEC is that IEC do not have any legal authority. So it's most of the time it's driven by the quality systems of the particular company, or it's driven, or it's like a contractual between a supplier and an end customer. The most popular standard in IEC are 61000 series. There are lots of standards in this particular series that addresses various popular instances of EMC. It also includes CISPR standards. International Special Committee on Radio Interference includes CISPR 11 and 22. There are two types of standards. Basic standard covers specific interferences, and then the product-related standards. Like if there is a XYZ product, maybe say an appliance-related standard, that may refer back to a basic standard like an EST or EFT standard. Now, if you just look at some of those popular standards in 61000 series, in 61000 series, first one is like EST, S4-61000-4-2 is EST or electrostatic discharge. -4-3 addresses radiated electromagnetic field, and -4-4 addresses EFT, electrical fast transient or burst. That's 5 addresses surge or indirect lightning. That's 6 addresses RF conducted disturbances. And that's 11 addresses voltage dips and interruptions. 60601 is mainly designed for medical electrical equipment. So if you are designing a medical equipment, you may refer to this standard, and this particular standard may refer to rest of the standards like an EST or EFT or surge. So first one is the product standard, and rest of the ones are environmental related standards. Now if you look at IEC standard CISPR, 11 addresses industrial, scientific and medical radiofrequency equipment, 14 addresses electromagnetic compatibility requirements for household appliances, electric tools and similar apparatus, and 22 is for information technology equipment. The next category of standards is military standards. Again, military standard focuses both on emissions as well as susceptibility or immunity. If you look at the military equipments, they vary a lot, like from submarine to outer space, desert to Arctic environment. The military system, they require mission success. So at that time, if suppose it interferes with the TV communication or radio communication, that's not that important. But you should not lose the radio communication between two systems, or like your tank shouldn't get crazy if something happens in the environment. So that's why for each equipment or system, there are different level of standards. Most of the standards are contractual or negotiable. So depending on the equipment and person or end requirement, like if the government is buying from XYZ supplier, they will pose a requirement in a contract that they need to meet these many requirements. So most of the standards are application specific and can be negotiated. The MIL STD-461E is a key EMI specification. Next category is in a telecom standards. Telecom standards again focuses on both emissions as well as susceptibility. Includes various telecommunication equipment. Bell code GR1089 is again a key specification for telecom industry. Next one category is medical standards. In case of medical equipment, prime concern is reliable and safe operation of equipment. And many of these standards, like for particular medical equipment like FCC, do not apply for medical standard equipment. Here main focus is make sure it's reliable and safe, and again it depends on the equipment. Like you need much more reliability in a pacemaker rather than a heart monitor. If anything that is life critical, and if failure of that equipment cause a life-threatening injury or life, then it needs to meet much more stringent requirement than if it's used just for monitoring and then you can rerun a test. In US, FDA, Food and Drug Administration, controls the medical standards, but they do not create any medical standards. Most of the time they refer to an IEC 60601 standard. In Europe, IEC 60601 is almost mandatory. Again, standard depends on the application. Each maybe medical equipment may need to meet different requirements. The next category is the vehicular standards or automotive standards. They are among the toughest standard in the world. If you look at an automotive, it needs to work from the coldest place to hottest place, maybe lowest, just next to the sea level, to the highest height. It has a wide variety of environmental conditions that it needs to work on it. Again, because the user or a person is driving the vehicle, it needs to be also is a safety critical. In case of automotive, again, there are so many standards, and it depends on the automotive subsystem. Like an airbag needs to have much more stringent standard than maybe a radio. These standards covers lot or most of the vehicles like planes, trains, automobiles. This electronic operates in extremely harsh conditions, and it's also extremely cost sensitive. And that's why it's one of the toughest thing to manage for a designer, where they need to meet one of the toughest EMC requirements, and at the same time they need to be extremely cost sensitive. It focuses on both immunity and emissions. If you look at some of the popular automotive standards, they are SAE J551 and J1113. Also some other standards like NCEST S20.20. It focuses for many for protection of electrical and electronic parts, assembly and equipment. Now if you are like many of our small customers that they do not have any quality systems or they are not following any of the standards, then you may ask, we are not following and do not have any such EMC requirement, or we do not need to meet some standard. Why do I care about it? Many of the EMC standards are focusing on environmental noise effect. Suppose if you are operating in an environment where you may have like a spark generators, igniters, arc welders, you may have say bad power conditions, you are using a switch mode power supplies or transformers power supplies. You are like in an industrial environment where you have large motors, RF heaters. Maybe in your system you are using relays, thyristor drives. All these components create lots of noise in your environment. And although if you are not referring to any EMC standards, you need to make sure your system works in this condition. If you use some existing standard, it makes it easier for you to test your product and make sure it will work in this environment. Otherwise, you need to find a worse industrial environment maybe, or worse environment for your product and do an on-site testing. And it's much more difficult to do a debugging in that environment because you cannot control, you don't know what kind of noise you are getting and how it's being coupled to your system. This is one of the most famous charts. If you look at this chart, the y-axis is cost of addressing EMC issues, and x-axis where we have various stages in your design, like concept, design, PCB layout, prototype, testing, and production. Now if you see, if you think about EMC at earlier stage of design, then cost of addressing those issues is really small. But as you try to address those EMC issues in a later stage of design, the cost goes exponentially high. And like if you try to address your EMC issues in production, the cost is just too much. And this is the main reason that drives these EMC seminars, that we want to address the EMC issues at this level, where we are thinking about a concept of a product, or we are just doing a first design of a product or PCB layout. Addressing EMC issues at this stage is just much cheaper than addressing at that later stage. And these seminars will give you tips and tricks and other information to help you in addressing EMC issues at earlier stage. Now, considering this is a huge subject, let us define our objectives. What we want to achieve with the seminars. The initial seminars will focus on two EMC subgroups. That is a part of a second definition where it says it is not susceptible to emissions from other systems, like electrical fast transient. You may see this thing in depending on your environmental condition, and electrostatic discharge. And the third EMC subgroup does not cause interference with itself. And in this case, we look at something like inductive loads, connectors, cables. So that will be the main focus for initial seminars. And at a later stage, we will also look at the first subgroup. Now, when you're looking at the seminar, our focus applications are cost-sensitive applications that use a single or two-layer printed circuit boards. We may not focus that much on, say, 6-layer or 8-layer board design. They're looking at a typical application which uses a microcontroller and some digital glue logic. It uses some analog block. It does some power control, maybe through relays, triacs. It may be use a transformerless power supply or switch mode power supply. And how we go about it? First, we'll explain you all the fundamentals. Then we try to provide you simple, low-cost tips and tricks for a schematic, component placement, and PCB layout. We mainly use cheap on mainly passive components. We'll also explain how to select components. You may use the same capacitor, but what type of capacitor and what value you use may make a big difference in EMC behavior. So now if you just try to look further in future, so what's coming? What are we going to see in these EMC seminars? We'll have more detailed look on EFT and particularly one of the IEC standards 61000-4-4. Same way we'll look what is ESD, and we'll look at one of the IEC standards 61000-4-2. And we'll go into more detail in some noise fundamentals, of theory of noise. Then we'll look at various transformerless power supplies, how to select components, what kind of components you should select, what type, what values. So that will be one of the topic. And we'll go into a PCB layout fundamentals, and then there will be lots of tips and tricks. And in the end, we'll use some of those tips and tricks and the fundamental theory, and we'll apply into some design, and we'll have some case studies where we will see a before and after picture, and we'll see what kind of performance difference we get. This is just some basic overview of what's coming in future, and this is considering this is a huge subject. There will be so many subjects and so many topics, and you will see so many interesting things in upcoming seminars. So looking forward to see you for upcoming EMC seminars. Any questions, comments, feel free to give us all your feedback. Thank you.